Welcome back. Today we are going to explore a crucial concept in electrical circuits, the difference between electromotive force and potential difference. Let's start with EMF, which stands for electromotive force. EMF refers to the potential difference across the terminals of a battery when it's not connected to a circuit. To better understand the difference between the EMF and potential difference, let's conduct an experiment. Connect a cell in a circuit having resistor R and key K. A voltmeter of very high resistance is connected in parallel to the cell. When the circuit is open, the voltmeter will measure the EMF of the battery. That's because there is no current and hence no internal resistance affecting the voltage. Now, when we close the circuit by turning on the key, the current starts flowing. But guess what happens? The voltmeter reading decreases. Why? When the circuit is closed, the current flows through the cell. The cell has its own internal resistance, which causes a voltage drop inside the cell, opposing the flow of current. This means the voltage across the external resistor is lower than the EMF. We can express this relationship mathematically. E is equal to V plus IR, where E is the EMF of the cell, V is the potential difference across the external resistor, I is the current flowing through the circuit, and R is the internal resistance of the cell. So, as you can see, when current is flowing, the EMF of the cell is always greater than the potential difference across the external resistance unless the internal resistance is 0. Now, what affects the EMF of a cell? It depends on three main factors: the electrolyte used inside the cell, the material of the electrodes, and the temperature of the cell. Interestingly, the size of the cell doesn't affect its EMF. Whether you have a big cell or a small cell, if the electrolyte and the electrode materials are the same, the EMF can be same too. However, larger cells have higher resistance to current flow, but they can be used for longer time. Now let's see a practical example. When the current drawn from the battery is 0.5 ampere, the potential difference at the terminal is 20 volt. And when current drawn from is 2 ampere, the voltage reduces to 16 volt. Calculate the EMF and internal resistance of the battery. Let E be the EMF, R be the internal resistance. When the current I flows is drawn from the battery, the potential drop across the battery is IR. So we can write total voltage potential drop across the battery as E minus IR. First, for I is equal to 0.5 ampere, we see that V is equal to E minus IR. This is given as 20. We need to find E. I is 0.5 R. Let this be the first equation. Next, for 2 ampere. E minus IR. So the voltage reduces to 16. E minus 2R. This will be the second equation. So 20 is equal to E minus 0.5 can be written as R by 2. So which is 40 equal to 2E minus R. The first equation is 2E minus R is equal to 40. Multiplying the second equation by 2 is 2E minus 4R is equal to 16 2s are 32. So simplifying, subtracting this whole, we get 3R is equal to 8. R is equal to 8 by 3, which is 2.67 ohm is the internal resistance, and from this we can calculate E is equal to 2R plus 16, which is 5.34 plus 16, which is 21.34 volt. So this is the internal resistance and this is the EMF. Now that we understand EMF and potential difference, let's move on to the types of chemical cells which provide the energy for our circuits. There are two main types, primary cells, secondary cells. In primary cells, the chemical energy is directly converted into electrical energy. However, as we use the cell, the material inside is consumed. So once the chemical reactions are complete, the cell cannot be recharged. Examples include dry cells, Daniell cells, and voltaic cells. On the other hand, secondary cells store electrical energy as a reversible chemical reaction. When the current is drawn from the cell, the chemical reaction runs in reverse, restoring the original substances. This means you can recharge secondary cells. Acid accumulators like the ones in car batteries and inverters are classic examples. So to wrap up, EMF is the potential difference when a cell is not connected to a circuit, and it's higher than the potential difference across the external resistor when this current is drawn. The internal resistance of a cell causes drop in the voltage when current flows. Primary cells are disposable, while secondary cells can be recharged and reused. Thanks for watching. If you enjoyed this video, make sure to like, share and subscribe.